Well, tonight we're going to look at some monster shortcuts with regards to all the derivative rules, and then we're going to really start to apply that in as we write equations of tangent lines. The last day or so, we really grinded through the longer process of finding a derivative. So tonight we're going to cut to the chase and practice going really fast. So we're going to cover a lot of topics. We're going to start off by reviewing the power rule. Whoops, I'll try spelling here. The power rule, that's our favorite one. So we'll review that one. Then we're going to flirt with the product rule, as well as the quotient rule. The quotient rule is really interesting. We're going to look at different situations where we have to use it, and then we're going to look at some unique situations where we can try to avoid it at all costs possible. We're also then going to get into the much anticipated chain rule, which has the deepest implications as we go further into the year. And then we're going to review all of our trig rules. We've talked about sine, cosine, and tangent the last week or so, but then we're going to review secant and cotangent, and some other obscure ones. And then we're going to finish the night off with what WETL. We're going to really focus on writing the equation of tangent lines and deepening our comprehension in that field. Real quick review with that power rule. It says if we want to take the derivative where we've got an x and it's being raised to a constant power, what we're going to do is we're going to multiply the coefficient by n, and then now x is going to be raised to the n minus 1 power. So the biggest thing is just remembering to subtract 1 from that exponent. Now our first example tonight is one of those ones where you just want to be really patient and just rewrite it. That's supposed to be the fifth root of x to the fourth. And I can't stress this enough. Just take your time and rewrite the original problem before you try to take the derivative, all right? Rewrite, 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 rewrite. So as I get ready to rewrite this, I'm going to have a coefficient of 3/7, and my x is going to be raised to the negative 4/5 power. So, and again, at that moment, I haven't done 1 ounce of calculus, but now we're ready to apply that power rule. And what's going to happen is I'm going to take this exponent and multiply it by this coefficient, okay? So it's just a matter of negative 4 times 3 and 5 times 7. And then the most important part is we've got to remember to subtract 1 from this rascal. Now when I say subtract 1, in my mind I'm subtracting 5/5, which is going to give me negative 9/5. And then probably the last thing is we always want to mirror the original form that the original problem was written in. So we want to rewrite it in terms of a fraction with only positive powers. So I'm going to say negative 12 divided by 35 times the fifth root of x to the 9th power. Bingo. The product rule is, again, another very simple rule, and with just a little bit of practice and a little bit of experience, you can really master this rule. The other thing I want to stress is it's the product of two functions of x. So you've got one function of x being multiplied by a second function of x, and it is commutative, so the order can be played with and jimmied around a little bit here. So I'm thinking it's the first function times the derivative of the second function plus the second function times the derivative of the first function, okay? And as you see there, the plus sign and all these multiplication signs, those are all commutative, so sometimes our product rules might look slightly different on the surface, but they're all equivalent. So let's take a look at a couple of examples where it may and may not be applicable. We'll talk about example number 1, let's say x sine of x, versus example number 2 where we say 4 sine of x. Now technically the product rule is going to work on both of these, but I think you'd all agree if we use product rule on this function right here, it would be massive overkill. Because that first function is just a constant and as opposed to a function of x, it's really unnecessary. But then when you look at this example right here above it, what you've got is you've got your product sign sitting right here, and your first function is a function of x and your second one is a function of x, so there's the product rule being absolutely mandatory. Quotient rule is very similar to that product rule in that just a little bit of practice really will take us a long way here. However, the thing you want to watch out for is the quotient rule is not commutative, and the order in which we do everything is going to be extremely important. And so what we're going to do is we're going to start off with the low function multiplied by the derivative of the high function minus the high function times the derivative of the low function, all over that low function squared, all right? And the visual image I have in my mind is we're always going to, it's low d high minus high d low all over low squared. And it's just my image I have in my mind is I'm starting at the very bottom of the mountain. I'm going to climb my way up the mountain and then climb my way back down the mountain. So we're always starting low and eventually finishing low. And let's take a look at a couple of really key examples here. Let's see here. Let's talk about example number 1 for our quotient rule. If we said something like y equals x over radical x plus 1, what you'll notice is both the numerator and the denominator are functions of x. So the quotient rule is absolutely crucial. The only thing you could do, and I don't think this would be beneficial, is to rewrite it as x plus 1 to the negative 1/2. But then you'd have to use product rule to derive it. Now you're messing around with a lot of negative exponents and stuff. So I don't think the product rule would be beneficial, but it is doable. Example number 2, though, what do you think about this? What if I said 4 over radical x plus 1? Now, what I want you to get in the habit of is, because your numerator is not a function of x, and it's just a constant right here, I want you to really avoid the quotient rule on this one. And let's rewrite it as 4 quantity x plus 1 to the negative 1/2. And then all you need to do to derive it's the chain rule, which we're going to review in the next slide. And that's going to be a lot more efficient and less prone to careless mistakes. The third example is one of my favorite ones. And I want you to look at consider like a binomial or a trinomial in the numerator, like maybe 5x cubed plus 3x squared, and maybe it's being divided by x. So what we call is, I call this, we're going to make like a beaver and split it up. Okay? In other words, whoops, I definitely don't want that fraction bar, that's what I'm trying to avoid. I'm going to break this up and I'm going to say 5x cubed divided by x plus 3x squared divided by x. And I think you'd all agree that that's a very legal move. And as we simplify that, it turns into 5x squared plus, let's see, 3x. And now deriving that function is just be 2 iterations of the power rule, and it's much, much easier. So what I want you to do is start to look for, anytime we've got a monomial in the denominator, we're going to make like a beaver and simplify that expression so that we could avoid the quotient rule. And again, it's more efficient and less prone to careless mistakes. And now for the much anticipated chain rule. And I believe that this chain rule is, or this particular derivative rule, is more important than all of the others put together. The first thing is that we have to recognize the composition of functions, the fact that we have an inner function named g of x and an outer function named f. And as we derive them, let's see, we're going to start off by deriving the outer function while leaving the inner function untouched. Okay? Now, once we finalize the derivative of that outer function is the time where we multiply by the derivative of that inner function. The key to this rule is not getting in a rush, and you want to make sure you don't touch or derive that inner function until it's the appropriate time. So just be patient, finish that outer function's derivative, and then derive by the inner function. Okay, so let's take a look at a couple of examples. And we're going to just, a couple of these first examples are going to be really basic, just to get our feet underneath us and to make sure we all agree on the process here. And I want to take the quantity 3x plus 1 and then we'll raise it to the 4th power. So as far as identifying the inner and the outer, I would say the outer function is this quantity raised to the 4th, and my inner function is that 3x plus 1 rascal. So we'll get ready to derive it, and I'm going to take the derivative of the outer function. Notice I haven't touched the 3x plus 1, and I've got a cube for my new one. So at this moment, I've completely derived the outer function times, we'll derive the inner function and get a 3. And then the nice thing, probably the only thing you do is multiply that 4 and that 3 together to get a 12. And other than that, there's really not much cleanup on these rascals. Alright, example number 2, let's take a look at y equals the sine of x squared, okay? So my outer function is the sine of something, and my inner function is going to be the x squared. So the derivative, let's see, derive the outer function, and meanwhile we're not going to touch the inside. Alright, now it's time to derive by the multiply by the derivative of the inside, which is my 2x, and boom, ladies and gentlemen, we're done with that one. And let's see if we can sneak one more under our belts here. What if I just move that squared sign just a little bit and put the squared sign right there? Okay, really helpful move is to rewrite this as the quantity sine of x to the 2nd power, and that's going to help us a ton. And the outer function is going to be the quantity squared, and my inner function is going to be the sine of x. And so getting that derivative, it's going to be 2 times the inner function untouched raised to the first power times the cosine of x. And of course that 1's unnecessary, we just put that there for emphasis. Why don't we jack it up just a little bit, and we'll try one more where there's an outer, an inner, and a middle function. Check out this obnoxious rascal right here. Let's say y equals tangent to the 4th power of radical x, okay? And again, I'm just going to rewrite this rascal just so I feel a little more comfortable with it. It's going to be the tangent of x to the 1/2, and that entire expression is being raised to the 4th power. So, here we go. My outer function is going to be quantity to the 4th. My middle function is going to be the tangent of somebody. And my innermost function is going to be that x to the 1/2 power. And I just need to be real methodical and very patient as I go through this derivative here. All right. So let's see if we're ready to rock and roll. First thing I need to do is I need to derive the outer function. And while I do that, I cannot touch the middle or the innermost function, okay? And my new exponent is a cubed. Once I put that cubed on there, I'm done with my outer function, and now I'm going to derive my middle function, which is going to be that we're going to say the derivative of tangent is secant squared of, and you cannot touch that innermost function yet. Okay, now I've finished deriving the middle function, and it's finally time to derive the innermost, and I'm going to say that's 1/2 times x to the negative 1/2 power. And of course, we could clean that up a touch. You know, maybe we could put this x to the negative 1/2. We could rewrite it so that's in the denominator with a positive exponent. But other than that, there's not much to do. Of course, we could say 4 times 1/2 is really a 2. But other than that, that's how it goes. All right, now it's we're time to talk about writing the equation of tangent lines. And this particular point right here, we would say that the line is tangent to the curve at that point. That's called our point of tangency, okay? Point of tangency, just so we're using all the same vocabulary and such. All right, now the slope of that tangent line corresponds to the instantaneous slope of the curve, okay? Because I think we'd all agree that this curve has an infinite number of different slopes because there's an infinite number of points along the curve, and each point has its own unique slope, and so we call that the instantaneous slope. Okay. All right, now, in order to write the equation of this green line right here, we're going to use the point-slope form of a linear equation, and all it says is y minus y sub 1 equals m times the quantity x minus x sub 1, where, let's see here, of course, m represents the instantaneous slope at that point, and that's why we need to use our derivative so that we can calculate that instantaneous slope. And then, of course, the other thing there is the x sub 1 and the y sub 1, that just happens to be a point that the line passes through. So we need two key ingredients. We need to know the instantaneous slope, and we need to know a point that the line passes through, and bada bing, bada boom, we'll be able to cook up that equation of the line. Okay, so here's a standard set of what the directions might look like, and they're asking us to write the equation of the tangent line of the function at a given value of x. And the function that I want to start off with here is the tangent squared of x. And I want to write the equation of the tangent line at x equals pi over 4. So that's a pretty friendly x value to work with here. Alright, now as far as the derivative goes, I'm going to be really patient, and I'm just going to rewrite the original function as the tangent of x squared. And in fact, we could go find, before we worry about the instantaneous slope or anything like that, we could finish off the point and just try to find the corresponding y value. And if we substituted a pi over 4 into this x, the tangent of 1, or I'm sorry, the tangent of pi over 4 equals 1, and when you squared it, we still have a 1. So that part was very nice. Now as far as the derivative goes, we're going to use our chain rule, derive the outer function without touching the inner, okay, first power, times the derivative of the inner function. Now what I need to do is I need to evaluate the derivative at pi over 4 specifically. So I'm going to get 2 times a 1 times, oh boy. Alright, now I like to evaluate the cosine of pi over 4 in my head first, and then I'm going to reciprocate it. So the cosine of pi over 4 is radical 2 over 2, but if I reciprocate it, it'll be 2 over radical 2. And I'm not worried about rationalizing that number like we would have in Algebra 2 for two reasons. First of all, the AP exam says we don't have to have answers with rational denominators. And second of all, we're going to end up squaring it anyway, which is going to alleviate that problem. So it's 2 times, let's see, we're going to get 4 over 2, which is really 2. And to finish it off, we've got a slope of 4. So as I put this all together, the equation of my tangent line is going to be y minus 1 equals 4 times the quantity, x minus pi over 4. The best news in the world is that we do not have to clean these up. I'll repeat that. The AP exam says this is our final answer. We get full credit, so there's no real need to go any further. And if we do go further, we're proceeding at our own risk. And if I made a simple multiplication or any arithmetic errors as I went further, I would be deducted points. So as far as our classroom policy goes, we're going to say if you do go any further than this, I'll take points off because it's an unnecessary risk. Okay, here's our last problem of the night, and it's a rather obscure one. And here's what's given to us ahead of time. They've given us or defined this random function named g of x, and he's defined as the product of radical x and f of x squared. And then they happen to give us two other random tidbits of information. They said f of 16 happens to equal 8, and f prime of 16 happens to equal 1/4. And you're wondering why in the world did they give us that information? Well, we'll soon find out. What they want us to do, what they're asking us to do, is to write the equation of a tangent line to g at x equals 4. So as soon as they tell me to write the equation of a tangent line, I'm already thinking point-slope form. I'm thinking not only do I need my x value, but I also need my corresponding y value, and I also need my slope. So what I'll do is I'll go ahead and find that y value first and foremost. So g of 4 is going to be the square root of 4 times f of 4 squared, which turns out to be 2 times, and then f of 16 was that 8 that they gave me. And so we'll say 16 is my y value that I'm going to need later on. All right, next thing I'm going to need to do is I'm going to need to calculate g prime of x. Always find the derivative in terms of x first, and then we'll evaluate it at a specific point like 4. So the derivative, you'll notice, is going to require some product rule, and within the bigger picture of product rule, we're going to have some chain rule sprinkled in there, and power rule, of course, as we go. So I'm thinking the first function times the derivative of the second, and here's where I'm using my chain rule. So, times 2x. So you'll notice what I did there was I derived my outer, I did not touch the inner function, and then once I completely finished deriving the outer, I then multiplied by the derivative of the inner. Okay, plus the second function times the derivative of the first function. So I'm thinking 1/2 x to the negative 1/2 power. All right, we'll see if we can now evaluate this function at x equals 4. So we're thinking g prime of 4 is going to be radical 4 times the f prime of 16 times an 8 plus, I'm going to rewrite this one as a fraction, and I'm going to say f of 16 all over 2 radical 4. And let's see, we got a 2. The f prime of 16, I think they defined as 1/4. Actually, I'm going to go up and check just to make sure I didn't screw that up. Yep, 1/4. Okay. And times an 8 plus, let's see, f of 16 was defined as an 8 all over basically a 4. So let's see. 1/2, I got 4 plus 2, which equals 6. This represents my instantaneous slope, and if we put it all together, the equation of our line is going to be, let's see, that y value was a 16. All right, so y minus 16 equals the slope of 6 times the quantity x minus 4, and that's the equation of a line tangent to g at the point of x equals 4, and we would just consider x equals 4 to be our point of tangency. So we covered a lot of rules tonight. Thanks for hanging in there, and I'll catch you in class tomorrow.